and welcome back for another short video. This video I like to call normal and Z transformations. We've seen in the previous video that the male American population in the current years has height that's distributed normally with a mean of 69.5 and a standard deviation of 2.4. That's an example of a normal probability distribution. Females have height that's normally distributed with a mean of 63.8 and a standard deviation of 2.6. So female height is also normal, but it's not the same normal because it has different parameters. And just for the heck of it, I looked up German Shepherds. German Shepherds have a height distribution that's normal with a height mean of 25 and a standard deviation of 2.5 inches. So here are three normal distributions, but they're all quite different. And in fact, there's an infinite number of normal distributions. So if we were avoiding integrating by documenting in tables all these different normal distributions, we'd have an infinite number of tables, which would take a very large book and be quite inconvenient to haul around. Well, of course, tables is how we used to do it, and then we would only do tables for a few values of the distribution, or we would create a table of a standard normal distribution. Now, we've done Z transformation some time ago, and remember, if we have a value x, its Z value is x minus mu over sigma. Now I want you to think about a random variable x and subtract its mean and divide by its standard deviation and create a new random variable z. If x is normal mu sigma, then z is normal 0, 1. If x is normal mu sigma, then z will be normal 0, 1. Well, since we can transform any normal mu sigma into a z, that means we only have to have one table or one routine for calculating probabilities. We'll calculate probabilities for x by doing a transformation and calculating a standard normal distribution, a Z distribution. Let's do one we know. We'll let x equal the heights of U.S. males, and we know that that's normal with a mean of 69.5 and a standard deviation of 2.4. Let's find out what the Z value would be for x less than or equal to 72. If x is 72, let's backtrack a second. We know the probability of x being less than or equal to 72 is 0.8512. Now let's do the Z transformation. Transforming 72, we see Z is 72 minus 69.5 divided by 2.4, which is 1.0417. That's the Z value. The probability that Z is less than or equal to 1.0417 well, we'll use Minitab. Now remember, a Z is a normal 0, 1. So we'll come to normal probabilities and we'll change the mean to 0 and the standard deviation to 1. And our input constant, I had a mistake that Minitab caught. I inadvertently typed a standard deviation of 0, and it has to be 1. All right, I'll make that correction, 0, 1. And my input constant will be the 1.04 number. That's the z value of x equals 72. Say OK. And the probability that z is less than or equal to 1.0417 is 0.85122. That's exactly what we found for x less than or equal to 72. X less than or equal to 72 is 85.12. That is 85%. Z less than or equal to 1.04. That also we've just observed is 0.8512. So it would be sufficient to have a table or a way to calculate z probabilities and do the transformation. Now, in fact, with technology where it is today, it's really easier to just use the x values and not do the transformation. But this transformation was of immense value a few years ago when calculators and computers were not in everybody's backpack and on every desk. All right, more thoughts in a moment.